record again. All right, let's okay, so it's 0. Let me start. That's the next slide. Let's start from here. Okay, so okay, here we go. So now what we're going to look at next are products. As you can see, basically we're going to see some rules with exponents involving products. So if you have a real number, let's say, right? Let's just consider this example first. If you have a cubed times a squared, well, we already know what a cubed means, right? That's just a times itself 3 times, right? That's what I have here in parentheses. A squared is just a times itself, you know, a squared, 2 copies of a. But because multiplication is associative, we really don't need these parentheses. So let's take them away, and we have this. But how many a's do we have here? We have 5 a's, meaning we have a to the 5th. Okay, and 5 is 3 plus 2. Okay, so what's happening here? Really what I'm trying to illustrate is this wonderful rule, which says that if a is any real number, you have 2 integers, m and n. When you multiply like bases, you add the exponents. That's all I'm trying to show here. I mean, hopefully this example illustrates the idea why you can do this. Although it's really not too hard to see, but again, I'm just trying to illustrate this rule. That's all. And again, you know, it's good to see examples. So we have one here. 5 to the 4th times 5 squared, right? Well, again, what do? You add the exponents. And you get 5 to the 6th. I mean, if in a calculator you were to multiply and carry out the product, you would see it would be the same as 5 to the 6th. Just trying to illustrate this rule. Okay, that's good. Okay, that was a product. Well, let's look at a quotient now. And since we have a quotient, we do need a to be non-zero. So if a is non-zero, and first let's consider this example. So if we have a to the 7 over a cubed, right? Well, a to the 7, we just listed out, right? That's what this is equal to. A cubed, that's a listed out like this, right? 3 a's, you multiply them. But now a is not 0, right? Well, we need that because otherwise we would have 0 over 0, which doesn't make sense. But we can cancel. Namely, the 3 a's here in the denominator cancel with 3 a's up here in the numerator. Now, I didn't show the cancellation, but what ends up happening is you're going to get 4 remaining a's. Right? Because these 3 cancel with 3 up here, right? And what happens is you're left with 4 a's, which is a to the 4th. Okay, so a to the 4th, what's that? Make sure. To the 4th, we know is a to the 7 minus 3, because 4, 7, 3. Really what I'm trying to illustrate here is this rule. If a is a non-zero real number, when you divide like bases, you're subtracting the exponents. That's what I'm trying to show here. You're subtracting them. Okay? So that's what I'm trying to show here. And I just threw in I put an example in, as you can see. You know, we have 5 to the 6 over 5 squared, okay? And that's the same as 5 to the 6 minus 2, which is 5 to the 4th. Again, we're just subtracting exponents. That's all we're doing. Okay, let me just see something real quickly. Yes, I'm recording. Are there any questions, though? Are there any questions at all, or?
No.
Okay. Hope I'm not going too fast for anyone. Am I?
Oh, you're good.
Okay, now, remember how I said that a to the 0 is 1, right? If a is not 0, well, Mathematicians like to prove statements, so we're going to actually give a short proof why that's true, why a to the 0 is 1 for any non-zero a. Okay, so let's assume a is not 0. Well, if a is a non-zero number, then if you take that number a and divide it by itself, you're just going to get 1, right? Over here. You know, this, you could take anything and divide it by itself, you're going to get 1. Okay. Remember also from a previous slide, a to the first is just a itself. That's really part, I guess you could say, the definition, but, you know, we saw that earlier. Okay, that's good. Now, what we're also going to do is use a rule we just saw, where if you divide, you subtract the exponents. So here, I'm taking 1, replacing a with a to the first. But again, you're dividing like bases, so you subtract the exponents. What happens then? You're going to get a to the 0. So on the one hand, this is going to be 1. But what's also true is from here, you get a to the 0. Again, we're dividing, so you subtract the exponents. So that's why a to the 0 is 1. And again, here we're assuming a is not 0. And that would, and we need that because otherwise this would not make sense. A over a. Right? 0 over 0, it's not defined. You never divide by 0. So that's why you need a to be not 0. You know, I just thought I'm not going to ask you to restate this proof on an exam or something. You know, I just thought it'd be neat to show why something is true. All right, well, let's see some more exponents. So we're going to see some more rules now. So again, we have a real number a. Let's consider this. Okay, so here we have a cubed, and then we're squaring that product, meaning, you know, we're multiplying it by itself. So we have a cubed. We're doing a cubed times a cubed. Now, what is that equal to? Well, that's going to be a to the 3 plus 3, right? You multiply like bases, you add the exponents. You add the exponents. So this is equal to a to the 6, which is 3 times 2. And really, what am I trying to illustrate here? Well, I'm trying to illustrate this rule. Here, if you have a power raised to a power, you multiply. That's really what I'm trying to say. You have a power raised to a power. That's the same as multiplying, as you can see. Okay. And again, I just threw in 2 examples here. So 8 to the 4th, right? Well, that's the same as, since 8 is 2 cubed, that's the same as 2 cubed raised to the 4. There's a mouse. Now, using this rule, you can multiply the exponents, right? So you get 2 to the 12th. Same thing, same idea over here, 4 to the 10th, right? Well, 10 is 2 times 5. So this is the same as 4 to the 4 squared raised to the 5th. And that's also the same as 4 to the 5th squared, right? And that's just equal to this. I just threw that in there just to demonstrate the rule. Again, you probably have seen the rule before. If you haven't, that's okay also. So, and some other rules I want to point out. So here we're now going to look at 2 bases, not just 1 base. And this is the first rule we see. So if you have a product a times b, and you raise that to the n, you get a to the n times b to the n. And really, one of the main reasons why this is true is because multiplication is commutative. In other words, you can multiply in any order you want. And that's one of the main reasons why this is true. Okay, so this is with products. What about quotients? Well, that's what we have here. So here we have a over b to the n is a to the n over b to the n. And let me just say this, the book does this. Whenever you have an equality like this, you're assuming both sides here exist. You know, remember from before, if the denominator is 0, right? You don't divide by 0, so this would not make sense. Well, here we're implicitly assuming b is not 0. It's a convention the book takes. I figured it wouldn't hurt to say it here. And this is just a special case of something that I thought would be good to present. If you have a over b to the negative 1, right? Okay, well, that's the same as 1 over that. Negative exponent, 1 over it, right? This is the same algebraically as this. So altogether, if you raise something to the negative 1, a fraction that is, you flip it, like so. In other words, you take the reciprocal, is what I'm trying to say. And again, it's good to see some examples, so I threw some examples in here, right? So we have 3 over 2 to the 4th. That's 3 to the 4th divided by 2 to the 4th. So I'm using the second rule here, right? We have a fraction raised to a power. And, you know, if you carry out the products, you get 81 over 16. Here, I'm using the bottom rule here. If you have 3 over 2 to the negative 1, right? You just invert it. That is, you flip it. You get 2 over 3. That's all I'm trying to say here. Let's do another slide. So now this is just another warning I wanted to present. I've seen people make this mistake, so I want to make sure no one does it here. If you have a plus b raised to a power, okay, you know, raised to the n, this is not necessarily going to be a to the n plus b to the n. You know, in other words, addition does not behave as nicely as multiplication here. So a plus b to a power may not be a to the power plus b to the power. I mean, if n is 1, then yeah, it's going to be true. But if n is not 1, it may not be true. Just to illustrate that, well, let's consider 1 plus 3 squared, right? 1 plus 3 we know is 4, right? So 1 plus 3 squared is 4 squared, which is 16. Okay, so that's good. But 1 squared plus 3 squared. Well, 1 raised to anything is 1. 3 squared is 9. So here we get 10. So over here we would get 16. Here we would get 10. And 16 is not equal to 10, of course. So this does not have to equal to this. Oh, sorry. Sorry, I went too fast. So here we go. Okay, let me move on to some other examples. I like to put backup examples here, so I'm not sure if, I hope these are on the slides. I can always repost the slides if necessary. But this is just another one I did, 10 over 9 cubed, right? That's the same thing as 10 cubed divided by 9 cubed. 10 cubed we know is 1,000, right? 9 cubed is 729. Now, if you were to, instead of to the third power, raised it to the negative 3, what would happen is you would end up flipping it. And the next line actually kind of illustrates it, although I guess this could have been better, but it's just some other stuff I decided to put in. So, okay. So I figured it wouldn't hurt to do these examples. As you can see here, all I'm doing is 10 over 9 to the negative 3. And this negative 3 we know is 3 times negative 1. Okay, so, but then using a previous rule when you're multiplying exponents, that's the same as raising to a power, raised to another power, like so. Okay, and then I just wrote it another way. So, I mean, hopefully this helps. I mean, it's just something else I wanted to point out. So, hopefully it makes sense. Okay, good. Again, this is just review. In the past, I have reviewed fractions. For time consideration, I'm not going to do that. But I did post a video on Blackboard where you can, which actually reviews fractions. So it's just something I wanted to point out. So let me stop recording.